The last talk of the morning session is Carola-Bibiane Schönlieb. Okay. I'm sorry, my German is non-existent. She is a professor here at Cambridge, and she will tell us about image analysis and how that can be used for art restoration. Thank you.
Thank you very much, and thanks a lot to Andre and the organizers for inviting me. So the first thing I would like to get a sense of is what is the audience like? How many of you are mathematicians? Okay, that's fine. So mathematicians, physicists. So the basis of this presentation is actually a public lecture that I gave. It's a bit squeezed, and so in danger of embarrassing myself with respect to the mathematicians, I will try to keep things simple and conceptual. Okay. Yeah. Okay. Thank you. Okay, so let me just say that what I'm going to show is joint work with a couple of people who I worked with along the way, and they will appear on the appropriate slides, just to acknowledge them already here at the beginning. Okay, so what do I want to do in this presentation? I would like to discuss the idea of using mathematical formalism to interpret or to understand how art is formed, how we can use mathematics to formalize how an artist maybe paints. And why I'm interested in this is because I would like to use this mathematical formalism then to create algorithms which digitally restore paintings, frescoes, illuminated manuscripts. So these will be the examples I'm going to show. And so this is just a teaser. I didn't work on this myself, but just because this is, a very recent example of where art restoration had a huge impact on this recently discovered Leonardo painting, which was sold for this very amazing price of, I think, $450 million or something like this. Okay, so to give you a bit of a background, the first time I actually encountered art restoration was during my PhD, which was in 2005, when we had a project in Vienna on the restoration of the so-called Neidhardt frescoes. And that was, I will tell you a bit more about these frescoes in a minute, but that was a collaboration between actual conservators who were at that time physically restoring these frescoes and us mathematicians trying to find a mathematical way to automate this restoration digitally. So to create a virtual template of what the restoration could look if you do this or this. So these Neidhardt frescoes, they are medieval wall frescoes, one of the oldest incidences of profane frescoes that we have. And they are located in an apartment in the city center of Vienna. For those of you who know Vienna, this is in Tuchlauben. And they depict scenes that appear in the stories that this Minnesinger, and again, actually I always forget what Minnesinger is called in English.
Minstrel.
Minstrel, thank you. They depict scenes of the songs of this Minnesinger Neidhardt von Reuenthal. And so Neidhardt in particular sang about profane things, things of everyday life. In particular also about things like relationships between knights and maidens and things like this, and those you can also see in these frescoes. So at one point in time, the Catholic Church got hold of this building, and they really didn't like that fact, and so they overpainted the frescoes. So this is an example where prudency really was very damaging to such a very precious example of medieval times. And so about 300 years later they were rediscovered, and they were rediscovered by removing the paint from them, this overpainting, but in this process they also removed part of the frescoes. And so this was the reason why they then wanted to physically restore them. Okay, so these are these holes that the conservators wanted to restore. So this is really was the beginning of how I got involved in that. And the idea, as I said, was to apply digital restoration methods to create a virtual template of the restored frescoes. Okay, so before I tell you how this works on the frescoes, I will give a general introduction of what are the mathematical principles of digital restoration. Then I'll tell you about the frescoes and some other things that we have been doing recently with the Fitzwilliam Museum here in Cambridge. And maybe if I have time, but I might not, I'll tell you what relationship these digital restoration methods have beyond art. Okay, so again, so this is a public lecture, so I will start basic and I will speed up if I can feel a reaction in the audience. I don't really see you, so that might be challenging. But so if we talk about digital art restoration, we first have to understand what a digital image is. And so I guess all of you kind of know that this is really a quantization of the real world, and you can see what I mean by quantization by zooming into this JPEG photograph more and more, down to the level where you can actually see that this digital photograph is made up of nothing else than a collection of these little squares, which are my quantization squares, which are called pixels, and the visual impression we have from the picture comes from a color value, a color vector that is stored in each of these pixels. And here I've used the color space red, green, and blue. So once we understand that, we can put that into a mathematical framework by saying, well, a digital image is nothing else than a function that maps pixels, which I've phrased here in terms of coordinates, to intensity values. If I just have a grayscale image, these will be just intensities, let's say from 0 to 255. Or if I have a color image, it will be a vector valued mapping from these pixels to the RGB space, for instance. And and you can think about it in various ways. You can think about this as what you visually see as in the photograph. You can think about that a bit emphasizing that this is a function as a gray value surface over the xy plane, or you can just think about that as a collection of numbers stored in a matrix. Okay, so digital restoration now means, and now we can actually start doing mathematical things with this because we have a function, that we have an image given to us that I call f, and I know this image everywhere in this light gray domain, but the image is damaged, or I have some occlusion, or I have in general a hole, a gap in this image in this what I call inpainting domain D. And so the task is, based on the information I have about the image outside of this inpainting domain, and maybe based on some other expert knowledge that I have about this painting, can I restore the image inside of this inpainting domain? Can I reconstruct the function? So it's an interpolation problem, if you wish. Okay, so my background is in PDEs, and actually PDEs are one technique that has been very widely and classically used for this restoration task as an interpolator. And so this is where I embarrass myself in front of the mathematicians, but just to give you one example of such a mathematical object like a differential equation. One of the most famous ones is the heat equation, which when you apply the heat equation to an image, what you do is you embed this image into an evolutionary process. You start this evolutionary process with your given image G, which here in this example is just this random collection of intensities. And you let it run along this heat equation, so you evolve it over time. So this image now doesn't just depend on x and y, but also on time. And by doing so, what you're doing is that you are locally, you can think of, averaging the gray values more and more and more. And that is here an example if I run this up to a time t equals 10. So why would you want to do something like that? So let me give you a bit of a background of why you might want to do something like this. So first of all, this equation is called differential equation because it encodes derivatives of this function u with respect to time, so this is the evolution, and derivatives of u with respect to space. So why would that be a useful concept for images, to look at derivatives of a function? So if you look at this simple picture here of an eye, and you just look at the intensity profile along this, this one-dimensional slice here, then this looks something like that. So if I now think about that as a one-dimensional function, we can understand what derivatives are, and those derivatives, if I now simplify this profile, the derivatives, what they show, this is the first and the second derivative, what they show is the places where this grayscale intensity function is significantly changing. So these are indicators of where something interesting in the picture might be going on. And so if you generalize this to not just taking a slice, but actually to my two-dimensional setup, this is where these partial derivatives come in. And what you're doing is basically you take, for every pixel in the image, you take you take the derivative that we've just seen on the previous slide along the x direction. This is this one, and you take the derivative along the y direction, and this is this one. What I'm showing here is that you take the modulus of each of these values that you get, you add them up, and then instead of the intensity that I had before, I'm storing now this new value. And so what you see here is relating back to the previous slide, highlighting the places in the image where something significantly is changing. So this could be a first way to understand where maybe the more uninteresting areas in the image are and where something is happening. So this is a way of, if you wish, an edge detection. So how does this relate to the heat equation, where I want to somehow use this quantification of changes to start with an image and then process it by using these derivatives as a way of smoothing the image. And the nice thing about the heat equation is that there is a very nice relationship with what is maybe more widely known as Gaussian filtering that is very often applied to images, because the solution of the heat equation at a particular time t is nothing else than the convolution of the initial state, my initial given image G, with a Gaussian kernel, where the width of this Gaussian kernel is proportional to the time I'm evolving this image along the heat equation. And this slide I have to explain convolution, but I think convolution is maybe something that people know. So this is really about taking local averages, and depending on my standard deviation, I'm taking local averages in larger and larger regions. And so the effect that this has is, if you start with an image like this, and you convolve it with a Gaussian filter, let's say with a standard deviation of 2, you get something like this. If you convolve it with a standard deviation of 5, you get something like that. Which means that what you're doing is that you are starting with a picture with an image G with all different scales, fine scales to large scales represented in it, and when you run it along the heat equation, you're going into what is also called the scale space of this picture, which filters out more and more the smaller scales and only captures the larger scales in this image. So why do I go on about this? Doesn't look that great, but actually, and this is just to show you the comparison with involving an image like this along the heat equation instead of Gaussian filtering, you really get the same effect. So why do I go on about this? Well, because the mechanism used in the heat equation, this local averaging, or how we also like to call this diffusion, is something that we can use for this restoration task. And we can use it in the following way. Now think about, this is my photograph here. My damage domain, my inpainting domain, is the domain of these black squares here. And what I'm doing now is that I'm solving the heat equation only inside of these squares, taking as an input for the diffusion the gray values in the surrounding of this. And what this then does is that it's somehow diffusing those gray values into the damaged parts to create something like this. And that doesn't look too bad. Well, this is just to show you that this is really an evolutionary process. So you're starting with an initial guess G inside of your damaged domain, and then you're evolving the heat equation with boundary values, with the intensities, or in this case the color values given in the intact part of the image. Okay, so if the heat equation would be the solution to all of our problems, if that would be really the right mathematical formalism to understand how structures are propagated, how a painting is completed if you have a gap, then we wouldn't need to go on. Then a lot of us would be out of business. Well, this is not the end of the story, because as you have seen also in the initial pictures I've shown, diffusion is a very simple process. It is in particular a homogeneous process which is independent of the structure. If you are in a region where you have a very large derivative, where you have an edge in your image, where there is some interesting structure, or if you're in a homogeneous region, the diffusion, the amount of diffusion that is applied will be the same. And so this is the reason why people have thought about more sophisticated approaches along the similar lines, but looking at a bit more sophisticated differential equations. In particular, to avoid this blurry effect that is just local averaging is doing, and also as a result to be able, if you have, again this is a very simple restoration example where this is the intact part of my image and this gray grayish circle here is my gap that I want to fill. If I just apply diffusion, then I will never be able to propagate structures properly. And this is one of the main mechanisms, if you think about this, how you might want to restore art.
Question?
Yes?
The diffusion is only from the edges of the damaged boundary, or is it from further?
Okay, so you can do it in two ways. One of them is, as I said, just solving the heat equation inside of your little squares, and then you only take the intensities at the boundary of your domain. Or you do it in a weaker way, which is you solve the heat equation on the whole picture, but you have an additional term in your equation which forces the picture to stay close to your given picture outside of the inpainting domain. So in this case, it's a weak form of boundary conditions. Does it make sense? Okay, so if we want to design more sophisticated restoration approaches, we have to think how on earth should we actually restore paintings? And I don't know how many of you know this. Yes. So what is a desired inpainting? If you look at this and you look at how it looked originally, maybe that's not the right way to do it.
Has he just been on a fight?
Yes, it looks a bit like that. But I think she was very proud of what she did and she got famous with it. So on the other hand, maybe more something like this is more appropriate than something like this. And this is a particular instance of a more sophisticated inpainting procedure that goes well beyond the heat equation. And I will tell you very briefly how this works. So how can we, in the first instance, create differential equations that capture how conservators are, or how on the one hand conservators are restoring paintings. So that seems a reasonable thing because they have done this for ages, so they must have a strategy of how they do this. And on the other hand, and this is also something that has driven this inpainting business a lot, is the question of how we as humans visually restore and close gaps in images. So interesting is also that one of the first works on differential equations in inpainting by Bartolomeo and co-authors actually the paper starts with saying, look, we went to our local museum and we talked with the conservators of what they do. And then we came up with this PDE, which somehow should mimic what they do. So they really took this approach. And the main points that they tried to formalize in what they did were these two things. On the one hand, is how do you recreate structure inside of the inpainting domain. And the idea is that you look at the surrounding, of course, that makes sense, and if there is structure which is arriving at the boundary of this inpainting domain, you might want to propagate this structure. And how do you propagate it? Well, what you want to do is that if you have constant grayscales, so lines of constant grayscale in the image which arrive at the boundary of this inpainting domain, like an edge of an object, then you would like to connect this with the edge that arrives at the other end. So I'm only talking about structure here. I'm not yet talking about texture because texture will be yet another business, and I'll get to that. So this is really to get a rough sketch of how inpainting or how restoration works. So you see structures at the boundary and you try to interpolate it. And that is one example of a more complicated differential equation which is doing this. And here the crucial thing is on the one hand you're going away from the homogeneous linear diffusion of the heat equation and you make it nonlinear, which now means that you are actually taking into account the structure in the image. What you're doing is that you're not diffusing everywhere in the same way, but if you have a significant structure, which I said is encoded in the derivative of your function, then you're diffusing less. So what this is the derivative in 2 dimensions, and you take the modulus of this. If this is very large, which means you have something significant happening, then you're diffusing less. And if this is small, then you're diffusing more. And the other thing is, if you want to propagate structure, taking into account on the boundary of your inpainting domain only the intensities might not be enough. But you might also want to pick up the direction from which these intensities are coming from, which is again encoded in the derivative. So you're picking up 2 things, and that results not just in a nonlinear version of the heat equation, but in a higher order, in a 4th order version of the heat equation. Anyway, so that then makes you actually change from what the heat equation is doing to something that might seem a bit more reasonable. And let me give you a more interesting result. So this is a photograph. The black heart here is my inpainting domain, and this is the result of applying this more sophisticated inpainting procedure. If I zoom into this here, where you see this is a region maybe which could be interesting because it has these structures here of the fold in the couch arriving, then this is the result of the heat equation, and this is the result of this more sophisticated approach. Now, I'm only talking about diffusion as a way to propagate structures or to restore gaps in images, but that is not the only thing that you could do. So this is an example of a completely different type of application. It's a more of, if you wish, a special effects application. So this is my former PhD student, Joanna. She's sitting on this stool, and what we did was that we applied this more sophisticated heat equation to get rid of the stool. So in this case, my inpainting domain is the stool, and then I'm using the color information around to get rid of the stool. And that's the result. So that's, we call this picture Mathematics Can Make You Fly. Quite appropriate for an Austrian where Red Bull is hosted.
Can you move back to the previous one?
Yes.
Okay, so there is a little bit of the stool leg which still remains.
Yes, so this is exactly, so if you now look into this region here, so let me go there. This is the result of this more sophisticated diffusion. So you can see it's trying to propagate structures, but it's diffusion. So it will not do it perfectly, and that's where you still see the stool. Now, why do diffusion? You could also do transport, for instance. So this means you are taking intensities at the boundary and you are propagating them along lines of constant intensity, which was one of the main principles that we have started out with. And that looks good. It has lots of other issues because it's transport. You can have shocks. So, you know, since it's not diffusing, it's transporting, and then from all sides, and then in the middle something must happen. And if these intensities do not agree, it might not look that good. So, here, for instance, you see that it doesn't look so great. But that's another mechanism you can think of, and this is captured by this type of differential equation that Bornemann and Merz came up with in 2007 for this. And these are 2 different versions of how you do this discretely. The main thing here is, what you do is that you are transporting your intensities along directions perpendicular to the gradient, which means along the lines where the intensity is changing least. And so this is along these lines of constant intensity. Okay, so now we talked about structure. And we learned how to do structure in painting from these conservators. But what about more complicated images where you actually have structures which are repetitive, where you have texture and patterns that you also would like to reproduce in these holes. So in this case, such PDEs that I've just presented, such differential equations, really do not work well because they are local. This is a local way of propagating things. It takes things from the boundary and it propagates them. But it cannot reproduce repetitive structures like the fur and the cat. And you can see that clearly here. Okay? So what to do then? And then actually the first instances of what people did here you can think of as a kind of intelligent copy and paste procedure. So that works in the following way. So this is my inpainting domain, my target region. And this is a very simple picture that I would like to use to propagate, to close the gap here. So how this copy and paste procedure works is that it works in terms of patches of the image. So you start at the boundary of your inpainting domain. You select intelligently a very important pixel at the boundary. So, and that is another part of this algorithm, how to select the really salient points of the boundary. And then you draw a mask around it. And what you then do is that you look for patches in the intact part for which the part of this patch at the boundary that is known is closest in some metric. And then this doesn't need to be unique, but you pick one of them, and then you copy it into, and then you go on and on and on and on like this. So you work your way forward from the boundary inside. And then you get something like this, which looks much better. And for the mathematicians among you, there is a connection of this. There is an energy formulation for this mechanism. There is a connection to non-local PDEs, but I'm not going there. And the last thing I want to mention is, in this world of learning and deep learning and everything, one can also think about ways to not just try to mimic what we have learned from expert conservators or what we know from visual psychology, but one could also think about maybe picking up new and possibly unexplored ways of how to inpaint. And there is a very nice recent preprint of Leo Horesh from IBM, where he proposes a machine learning approach which doesn't just give you the output, let's say the inpainted image, for instance, but it gives you an output which is actually an equation, which is, for instance, a physical model or something like this. So it works, it learns things on a dictionary that is made out of mathematical variables and operations that can link them to each other. So that's quite interesting. So then you could think of having a more interpretable way of maybe learning things that you don't know how you could use them for restoration. So just to go back to the frescoes, this is just to recapture this. So these are again the night art frescoes. And here what we did was a kind of two-step procedure to actually create a digital restoration of them. And what we did was we first reconstructed the structure, the main structure. So again, almost like art conservators would do, they first recreate the main things, the main geometry of the missing part. And this is given here. So this is not the same type of equation that we had before, but it's it's so-called Cahn-Hilliard equation here that we are using. And then based on the reconstructed geometry, you take this as a constraint to your copy and paste mechanism, and then you copy and paste, you synthesize the texture with this copy and paste approach based on this binary structure that you have recreated. And then this is the fully restored fresco in the end. Okay, 2 minutes, good. That's perfect, actually. Some more recent examples. So this is a collaboration with the Fitzwilliam Museum, and in particular with Spike Buckloff from the Hamilton Kerr Institute, which is our restoration institute in the university. And a couple of years ago now, actually, he came to me with this painting. And he said, look, Carola, I don't even know. I think this will take us a really long time. We don't even yet know how to start. There's so much lost here that and actually this painting is now physically restored, and I think it has been finished about a year ago, and I think the first time we spoke was 3 years ago or something like this. So it took them a long time to do it. And so in this case, you could think that something like a digital template of this would make a lot of sense. So here we had a very talented, actually at that time still bachelor student from ENS Cachan, who looked at this with us, and since this is extremely challenging, we first focused on, we were a bit more modest and looked at the less challenging bits of this. So I mean, just to tell you, we couldn't solve this whole problem. This is just too, this is really tough. So we focused on this shepherd here, and again, what she did was this kind of two-step procedure. By the way, here one of the challenges is already to detect the damaged parts in the painting. This is already quite challenging. So what we did here was first close the small gaps in the image with, if you wish, a type of heat equation approach. And then for the large gaps, we mimicked what we did for the Neidhardt frescoes, first recreating the main structures, the geometric structures, and then filling in the texture. And this is the result. And this might not look too bad, but it's still not good enough. The feedback we got from Spike is that this actually looks too good. So it's still, yeah. Another thing, and then I will finish, is a collaboration we have with Stella on illuminated manuscripts. So the interesting thing is, with illuminated manuscripts, they will never be physically restored. This is just not what is done for illuminated manuscripts. So digital restoration is the only way to visualize how things might have looked before. And this was one of the illuminations we looked at. This might not look damaged. And it's not damaged in the way we have seen so far, but actually this is another example where prudency took over. This manuscript was at some point altered. And it was altered by, I mean, what this shows is the story of creation, the biblical story of creation, Adam and Eve, and they were, of course, I mean, in paradise, naked, right? They were still innocent, and so these skirts, so the sleeve skirt of Adam and the veil of Eve have been overpainted, and that's something that they. So let's look at Adam. That's something that they actually knew already before, but then they used infrared imaging to look underneath the skirt, and that was good for us, because what we then did was we phrased this again as an inpainting problem, but an inpainting problem where there we used a kind of drift diffusion equation where the inpainting mechanism was guided by the structures outlined underneath the skirt. So you're diffusing, if you wish, along these lines, and this is the result. Well, this is the result after diffusion, and then again there was a copy and paste mechanism set on top of this to recreate a bit of the underlying texture, and that's the result in the end. That was part of an exhibition that took place in the Fitzwilliam Museum last year, and this doesn't happen to me often. Actually, it never happened to me before to be in the news, and so that was kind of nice, especially with the heading Adam and Eve naked again, and there is mathematics in the article, which is nice. And so I'll finish now by saying that it's interesting to see how mathematics for a task like digital restoration are actually trying to understand how painting mechanisms work and formalize them to actually do this digitally, to virtually recreate something that the artist might have done. We can use this to digitally restore all kinds of things. The practical impact is that art conservators can use this to create templates. Sometimes this is the only way to go back in time. And what I will not say is what I will not have time to go into is that this is something that is used in all kinds of other areas: medical imaging, geosciences, forensics, all kinds of stuff where closing gaps is essential. Thank you.
Right. Yes. In these types of approaches, do you always need to have information on the damaged, or to have a definition of the damaged areas? And a related question: could you use these to detect forging?
Okay. So the first question, the answer to the first question is, for the kind of methods that I presented, yes, you need to. Because actually just getting the domain on which you solve this PDE wrong a little bit, you're immediately propagating wrong information. That is different, maybe, with things like machine learning, because they can deal with contamination. And they can maybe auto-correct some of these things. But, yeah. And the other question was fortune. So, yes. So what actually a very famous mathematician, Ingrid Aubéchy, actually did a couple of years ago is to look at wavelet analysis for comparing forgeries with authentic paintings. And yeah, you can do things. Yeah.
So I was. You had said at the beginning that you're using maths as a tool, which is allowing you to do this. And in the previous talk, we talked about maths as a language. And you know, I'm speaking as an artist with a background in science, so I'm kind of happy with both. But I'm really interested in your thoughts on, you know, do you view maths as a tool or language or both, or when do you view it as that? So just thoughts around that.
So what was interesting is that one of the things that comes up again and again in this interdisciplinary collaborations is that Stella or Spike or these people, they say, why do they like this actually? And they like it because for them it's a kind of objective way, how to recreate things. It's objective in a way that is it's always following the same principles very, very strictly. It's a way to formalize this. So this is one thing.
Yeah, this is not art creation. This is art restoration, which is a very different field, of course. I mean,
right.
Yeah.
So, so I cannot claim that I create art. And there are people who kind of try to do this. And there is a very interesting series of conferences, which maybe some of you know, which is the Bridges conferences. Yeah, and there actually, I mean, yeah, but this is another story. It could be linked to that because in some way, I mean, you are starting with something, right? Your starting point is already art that is there, and you're trying to mimic that in a way to do the restoration. But it's not producing new art, although you can say, I mean, in painting, this restoration is very ambiguous. You will never know what was there at the beginning or originally. You just have a guess.
Good guess.
But then this area of art as a language, because that's speaking to art as a tool for, so, I mean, sorry, maths as a language versus maths as a tool. And I just wondered if you view, as a mathematician, you know, do you have a thought on that, whether maths for you is a tool or is it a language?
Well, for me, it's very much a language.
Okay.
For the conservatives, it might be more of a tool.
I have a question here.
You have indicated it a few times in your talk, but I think it's perhaps a very important point, which is that the prior expectation of what should be in the missing area is very important. And I think one example, say you have a portrait of the face, and the damage is where one eye would be. So, looking at it, you know here that there is an eye there. But the mathematics is not going to tell you that.
Well, okay.
Unless you have
unless you have more information.
The database.
Yes.
Of some sort.
Yeah, exactly. So this is also a good point. So think about this copy and paste mechanism that I've shown. You don't need to build your dictionary of patches just from the same picture, right? You could expand that.
Several pictures.
Several pictures, maybe several pictures of faces or several pictures of the same artist, of paintings of the same artist. And then you could do more than just looking, because, I mean, if you have an eye missing and you just have the information in this one picture, you will not be able to recreate it without additional information.
However, say you know it is a missing eye, so you can see another eye on the painting. So one option would be to sort of transpose the visible eye into the position of the missing eye, perhaps with modifications for and after that. But then that presupposes that it is an open eye, and this is not perhaps the portrait of Nelson, who lost an eye.
Pirate.
Yeah.
If you have no other evidence,
That's right.
then what
It
you
all-
have
it
in the
all depends
picture.
it depends very strongly on what you can know or hypothesize about what it should be.
Yes, definitely.
I have another question, and then
I have a
go to
question.
lunch.
Something I don't understand. In what you do, there's no danger. If it doesn't work, it doesn't work. If you mess up, you can try another method. But in the physical restoration, once they mess it up, it's forever. So why? What I don't understand is why they would, if in the cases where your method works well, why would they even take the chance? Why can't
To
they imagine
do
in a
physically.
museum having the damaged piece and then next to it a very high resolution digital print of your method? Why would they even try? Why would they potentially
Yeah, that's a
take
very
the risk?
good. That's a very good question. And that's the culture, right?
500 million.
Yeah. No, but that's a cultural question. So among, to give you an example, I mean, the illuminated manuscript are one example, and there the main driver for not physically touching them is also because they're very fragile. Thank you.
Chair.
But yeah, doing well. but with restoring paintings, for instance, there are also cultures, different cultures, people who are following different mechanisms of how to do things. For instance, let's say everyone is physically restoring them, but then there is the one culture which is physically restoring them where you never will see that this has been physically restored. Or there is the other approach to restore it, but to mark the areas that you are restoring with hatches, for instance, with little patterns that make them actually, you know, when you go far away, you might not see it, but when you go closer. And maybe with, you know, this is still not perfect. I think that's also one of the things, right? I told you this Sebastiano, this painting, we really couldn't solve that yet.
Yeah, but you can update. Next year you can make
Next
better
year you can
and
update.
digital print.
So I think once this is more evolved, it might be a path that is taken, I don't know.
And some of that may not be accessible with your method, because you know, some of the colors just age, and you cannot address the problem of painting aging. But if you know the physical, or the you know, physical process of aging, then you know how to restore the painting, and people know that, and they know what they can restore and what they cannot.
Well, so for the digital restoration, you capture one time snapshot, right, of how the colors are looking and so on. This will not age with the painting, that's right. But yeah.
Like mosaics, very old mosaic are easy to restore, actually.
Mm.
You could unage the painting then, what he means. Which is
Just one last question, and then we go to lunch because.
It's not really a question, but I work for the Fitzwilliam Museum and obviously been kind of involved in the Sebastiano, so I'm the exhibition manager, so I was involved in colour as well.
Yeah.
I think you're absolutely right that there is now, with the increased technology, there is a new kind of very strong counter argument to not restore things directly, and I think in the next 5 or 10 years it's going to really change conservation, and there is a lot of feeling about that within the community, because looking back, you have just the most awful historic damage that's been done and ways that can't be reversed now. And obviously this is fantastic, this digital. So, I mean, I think the other part of it, because my job is to I'm the exhibition manager, so I help to give the audience and our visitors a new interpretation of objects through exhibitions. One of the main things is having a way to actually show that information clearly to the audience, because that's clearly what people want. When they come to see a painting, you want the maximum people to be able to enjoy it. That's why conservation has happened historically. And I think, so one of the things that ran alongside Stella's colour project was this very in-depth digital sort of accessible website that meant that people could actually see all those stages. Otherwise, there really isn't any point doing it if people aren't able to access it. And that's the thing that's really changed in the last few years, I think. So it's a really exciting time for
So that's a very good example, because there it was written down a little bit what Eric said, because there the original illuminated manuscript was shown next to the digital restoration, in fact.
So you're actually you're making, you're actually giving a new layer of interpretation about the experience of you know, trying to understand the changes rather than just giving people a finished object to experience. Sorry, it's more of a comment than a question.
Yes, thank you very much. So let's thank our speaker again.